Asking an AI coding assistant to build an application requires it to manage every architectural layer, logic branch, and dependency in a single attempt. It produces a memoryless draft of the architecture and the implementation at the exact same time. As project files grow, the AI's context window fills up, older instructions are pushed out, and the model's accuracy rapidly decays. It forgets the original design constraints while trying to write the front-end components. Because there is no structured validation step in this workflow, if the initial architectural plan is flawed, the AI doesn't stop. It will confidently write thousands of lines of broken code based on a compromised foundation. Relying on a single-pass execution model creates fragile software. It shifts the burden of quality control entirely onto the user, requiring more human debugging and intervention than the tool originally promised to save. Supreme Team replaces this reactive approach. It is an AI skill system that runs inside existing coding assistants and encodes a strictly orchestrated, multi-stage software delivery lifecycle on the AI's output. The architecture relies on plain Markdown files. This simple baseline ensures the framework is platform agnostic and guarantees universal compatibility across any AI tool capable of reading skill definitions. At the execution layer, Supreme Team uses standard Python hooks to enforce deterministic environment interactions. Rather than trying to prompt the AI into behaving perfectly, these hooks physically govern how the AI interacts with your local system. This structure anchors the assistant within a state tracking system, creating an autonomous engineering team capable of managing complex, multi-day development tasks. The entire framework is governed by a single entry orchestrator known as Admiral. This is the mandatory front door. Every delivery lifecycle request must route through Admiral first. Admiral enforces routing rules using what the system calls doctrine, binding Markdown files that dictate how tasks are distributed. This shared vocabulary ensures the LLM cannot skip steps or bypass the pipeline sequence. The workload is first delegated to the design subpipeline. Managed by the commander skill, this phase is strictly responsible for establishing the architecture decisions and finalizing the API contracts before a single line of implementation code is written. Once the design is locked, Admiral hands the specs to the build subpipeline. Here, the build management skill orchestrates the actual implementation, writing the software and executing security hardening. Finally, the output enters the review subpipeline. The code chief skill runs bug detection and penetration testing, auditing the completed build against the original design contracts. Segmenting the workload across 47 specialized skills and 3 isolated phases prevents AI context exhaustion. The AI is forced to follow sequential engineering logic instead of guessing the final state. Between each of these phases, the system deploys adversarial gatekeepers. These act as mandatory validation shields, preventing flawed work from advancing to the next stage. There are 4 of these gatekeepers in total. 3 operate at the individual phase level to check the specific deliverables of design, build, and review. The 4th operates cross-stage under Admiral to ensure end-to-end alignment. Each gatekeeper relies on a deterministic Python engine to verify mechanically checkable facts, like confirming a required file actually exists, while the adversarial LLM evaluates the quality of the logic. The system operates on a strict rule. Approval is earned, never assumed. If a review claims to find 0 errors in a complex code package, the gatekeeper treats that result as highly suspicious and demands a re-audit. When a package is rejected, it is marked for revision and sent back to the previous node. A node gets a maximum of 2 revision cycles to fix the issues before the gatekeeper escalates the block to the human user. This adversarial friction ensures that no unverified code propagates downstream. It directly addresses the core problem of AI hallucination by mathematically forcing the language model to definitively prove its work. To overcome context window amnesia, Supreme Team offloads its state tracking from the AI's ephemeral chat history directly to your local file system. This is the persistent memory safe protocol. Every phase writes its discrete state, its audit trails, and its deliverables into a local directory in your workspace. To prevent concurrent session corruption, the system uses atomic write ordering and lease-based locking. The active session holds a lock with a continuous heartbeat, ensuring 2 instances do not overwrite the same progress. This design protects your project against unexpected failures. If your terminal crashes or you close your IDE mid-task, the active memory is safe. Upon reboot, Admiral instantly reads the saved state file. It recovers the exact pipeline boundary where the process stopped, allowing you to resume work seamlessly, even if you switch to a completely different AI coding assistant. By treating AI memory as persistent local files rather than temporary chat context, the agent ultimately gains true cross-session continuity. Surrounding this entire process is the runtime harness. This layer adapts the execution interface between the AI and your computer, regulating how tools are used without attempting to alter the underlying language model itself. At layer 3 of the harness, action realization, the system evaluates generated actions. It deterministically blocks dangerous commands and prevents writes into protected boundaries before they ever execute in your environment. Layer 4 handles trajectory regulation. It monitors the AI's behavior after execution, detecting degenerate loop patterns like the model repeating the exact same failing command or producing long streaks of empty output. When a loop is detected, the harness injects a precise recovery hint directly into the context window. This breaks the LLM out of its stagnation without requiring you to manually intervene or restart the session. While the gatekeepers are designed to fail loud to block bad code, the runtime harness is engineered to fail open. If a hook encounters an internal error, it steps out of the way and lets the action proceed, ensuring it never crashes your host IDE. Regulating the environment interface through these deterministic hooks provides strict guardrails. It is a highly reliable method for keeping an AI on track during long trajectory tasks, far more effective than just asking the model nicely to follow the rules. When we pull back, we see how these distinct layers interact. We have a central orchestrator, strict phase boundaries, adversarial validation, and persistent local memory. A software request enters through Admiral, gets strictly defined in design, implemented in build, and aggressively challenged in review. Only after clearing every gatekeeper does it become a finalized delivery package. This diagram illustrates the Supreme Team architecture, mapping the linear progression from the initial orchestrator through the 3 core subpipelines. The persistent memory linkages beneath the nodes anchor the entire lifecycle. Every phase writes down its state, ensuring no context is lost. This architecture imposes a fully managed, autonomous software development lifecycle onto what would otherwise be a simple sequence of reactive chat prompts. Let's contrast this framework with standard single-pass AI. Standard assistants operate on assumed trust and decaying context windows, spiraling into infinite loops. Supreme Team uses a phased pipeline demanding proof, a persistent safe protocol for resumes, and a deterministic harness to enforce safe execution boundaries. Scaling AI engineering output is not a matter of simply giving models more parameters or a larger context window. It requires giving those models professional execution infrastructure.